I'm Tom Trowbridge, and I'm joined by my co-founders, Evgeny and Dmitry. We appreciate your time. First, some housekeeping. Evgeny and I are going to give an overview of the platform, and then we're going to turn it over to Dmitry, our Chief Technology Officer and fellow co-founder, to give a technical architecture overview, and then do a demo and show exactly how easy it is to build and compose applications on Fluence. We want you to understand what we do and why, and how it works, and why it's important to you. And by you, we mean developers, but we also mean the general broader community in the rest of the world, because we think what we're enabling is important for everyone. For your viewing enjoyment, we're doing this all live. There is no net, so wish us luck. Some of you have heard of Fluence a while ago. We started in 2017, but for others, this is the first introduction to Fluence. So what have we been building over this period of time? We've been building an open application platform. What is an open application platform? It's a platform where applications share data and users seamlessly and without the risk of being cut off or disabled. And why is that important? It's important if we take a step back and think about how the internet developed. The internet brought about a great innovation by pulling together disparate data feeds, disparate data, and allowing people to collaborate across all kinds of platforms. And the innovation that was enabled has brought us to the world we live today. But over that period of time, we've seen a new model take place, a model that has really monetized the data extraction. And what that means is that large platforms have gathered data, they have monetized that data, and they've used those returns to generate excess profits, and then have built their developer teams, added more products, and made it impossible to compete. And if you look at a list of companies that you've all heard of but have gone away, you can see the graveyard that these internet giants have filled. And the list of companies that you haven't heard of that have died is even longer. And the list of companies that haven't even started because of the power of these large firms is even longer. And so what's more powerful, though, than these big internet companies? You are more powerful. The global developer community is far more powerful than any one company. And this brings up kind of a book by Eric Raymond, written in 1999, called The Cathedral and the Bazaar. And in that book, he argues that the original software model was built around a cathedral model, where a centralized authoritarian regime could create something wonderful, but it takes a huge amount of resources to collaborate and pull everyone together when you're in a hierarchical structure. And what he recognized, what open source really became the real poster child of, was the bazaar model. And in a bazaar, collaboration takes place among relatively autonomous actors, and they collaborate, develop without leadership, without overhead. And with that model, you can create things far faster and innovate far more easily. And I think we've all seen in the software world, the open source bazaar model really take hold and be the future of software. I know all of us are deep believers in open source, and this whole community is an open source community, and we can see the success that that model's enabled. But that model hasn't yet taken hold in applications. And that's what we're here to enable. And so if given just a chance, just an opening, some of the right tools, we think the global developer community can innovate and create a bazaar model, just like it has for open source software, but for open applications. And what are those tools? First, you need a distributed computing protocol to host applications in a way that you trust and know that your access and your data can't be turned off. You need to know that when you build an application, that application can't turn around and disable your access. That's critical. Second, you need a scripting language that makes it incredibly easy to build. We've built the Aquamarine language, which enables this. You need to be able to compose applications from existing pieces and existing code and existing applications very quickly, very easily, very simply. And third, you need to have an economic layer, a blockchain-based economic layer that tracks software usage and allows monetization of all the work, development, and innovation that goes into building these applications. And once you pull those three things together, you have an engine for a global ecosystem of innovation. And that's our mission, to empower the next wave of internet innovation. We want to make it easy and fun to build and rewarding as well. And to explain more about how we do this, I'll turn it over to Evgeny to go into detail on the building blocks and the actual mechanics of how it works under the hood at Fluence.
Hey guys, let's start from speaking about open application platform. And open application platform, what does it mean? It talks about open applications. And we said about composability and openness, but what do we mean by that? And how that works and why it's important and why it's better than the model that we have today with proprietary platforms. We define open applications as applications that decouple ownership from authorship. And it means that if developer creates application, it's not being hosted by developer. It's hosted by the other party, by other company or person, hosting provider, essentially. And it allows to decouple the control of running applications with users from the original author. And it allows to break that link, that platform risk, where developer can decide to first create an API and allow other people to build on top of their product, but then cut it off, like it happened between Facebook and Zynga, between Twitter and Periscope, and so on. Tom gave all these examples. And how it works today, I'm just a developer, like I built an app, I publish it, and then I host it. I cover hosting, I cover all the fees on the hardware, and I provide it for users. But I control everything, and there's no possibility to break this link of control. So how we do it differently? First, we allow applications to be hosted independently. There's a marketplace of hosting providers that can decide to host or not your application. And if developer creates new version of application or just a different application, there are hosters who decide to host it or not. If the new version of application cuts some integrations or API off, then hosting providers might say that for their users, it's more valuable to keep the previous version. And the previous version will continue to work because it cannot be just modified. It should be the new version. New version should be created and new version should be upgraded. And imagine that the developer created a new version which was not accepted by majority of hosting providers. So now you have two applications and they both works. The previous version with its users and new version with users who decided to use that. And this is the open marketplace. And this is essentially how blockchain networks works, where you have miners and developers, and they have to reach consensus on new versions of the chain, on new software updates, on new features. Miners can just say they don't want to run it. But in Fluence, it's more flexible. There might be different version of application exist at the same time, and they will all work, or just different applications served by different hosting providers. And second thing is we need to really allow developers to really easy compose applications, to iterate applications. So imagine that someone created a simple chat application that allows to send messages back and forth and published it on a network and it being run by hosting providers. And then another developer comes and says, okay, I developed stories feature and I will take my new feature and package it together with the existing service and we'll call it as a new application and we'll ship it to users. And some other developer can come and develop stickers feature and get another messenger app. So the applications can evolve this way. And what it means in terms of users and benefits for developers. Imagine that this is the audience, the users of the original chat app. And then when this developer published this this app to a network, opened it for other developers to build on top. And then they created their messenger applications and attracted new users by these new features. But how it works technically it's still new feature plus existing service. So the original chat application received new users, and the developer from the original chat application benefited from these new users because more users are using their application right now. And if there is a way to monetize these users, then the original developer can get money out of it. And more like the higher the stack grows, the more users attracted to low level, and the more value attracted to low level. And moreover, so the way how it works technically, there are services. Like every application consists of services. Like for example, chat can consist of chat service, the feature of group chat service, like it's another service, and there might be comments built from group chat service. There might be public channels built from chat service. They all might be created by different applications or different developers. And they may be packaged as a different applications again. So if I have just a chat service plus group chat service, I have WhatsApp. If I have all of them together, I get Telegram. If I think of them differently and have comments, public channel, and chat, I can have Instagram. And what also cool about this is the low level also is a part of this composing stack. So modules or services or databases, all kinds of tools that you use to create services also have authors. And these tools are reused across the network in many services, and then in many apps, and then in many apps building on top of apps. So even if you created a very small but very useful thing, it might be used in millions of applications. And if there is a business model again, then you can benefit from it. So the third thing that we need is business model. And the way how it works. On Fluence, customers or application developers themselves need to pay for hosting to hosting providers. But a part of this hosting goes to authors of all the components and applications and services used to build the final application. And this is coded in a blockchain. So this thing lives on a blockchain. So you cannot just say, oh, I'm not paying to author. The payment always coupled. The payment for hosting always has this author fee, the essentially royalty to authors of the applications and services and components that are being used under the hood in the application. And this all together essentially makes the open application platform. And the big thing of this platform, the composability that I described. And now we want to talk more about Aquamarine, the programming language and the stack that we created to compose applications and services over the network. And I'm giving the word to Dmitry, my co-founder. He will talk more about Aquamarine.
Tom described the high-level view of the open applications platform. And the key part of open application platform is the approach to composability, to composition. And I'm going to introduce Aquamarine, our approach to composition from the technical perspective. So first of all, a short design overview of the Fluence network. What do we need to have to build an open applications platform? First, we need to run services on some peers, on some machines. To do so, we developed the Fluence Compute Engine that runs WebAssembly packages and can access internal resources or external services. Then we need to compose these services secure way, reuse services and data. this is solved with Aquamarine that I will be talking about today. Security should be backed somehow. We have signatures, cryptographic relations, and a DPKI infrastructure implemented as a trust graph. Then, if we have services and resources and peers, we want to route to them and to find the resources. It's implemented with Kademlia and DHT in Fluence. Here we have Kademlia star and DHT star because these algorithms are augmented with the trust graph for better reliability. And finally, we need to have a blockchain for licenses and payments. But today, I will speak about composition. What is it? What can we want from composition? What behaviors should be available? So, for example, let's imagine the client, the web browser, that wants to do something, to use many services and compose them. First of all, it goes to a Fluence node that is connected to the network. Then it's very natural to move computations to some other node, other peer, to call a service here, to call a service function, and to have the result. So we have the sequential computations here. Then it would be nice to use this result as arguments on other peers to call different services in parallel. And if we have parallel execution, then it would be nice to aggregate the results of computations on some other peer and to call a function to aggregate with all the results of the previous steps. It's possible that the peer fails. The function may fail or the peer could be unavailable. And in this case, there should be a way to recover because it happens in the real world. And the recovery essentially is a part of a more broad problem of branching. So if a service failed, or if a predicate doesn't hold, then we want to do another thing, like move execution to another peer or try another service. And that's branching. So Aquamarine is the composability medium that makes all of this possible in the open network. So the developer can express choreography in a script, something like this, to do some steps in the network, get the results, call functions. The script and the data is being moved from peer to peer in a single-use logical network. So these peers, these services coordinate on a single request, forming a logical network that disappears when the request is handled. And finally, services provide Merkle proofs and signatures for their responses, and all the proofs are checked on the way. For the developer, it looks a bit different. So here's an example of AIR, the low-level language for Aquamarine. Here we have sequential computations, calling functions, doing parallel execution, and joining finally. So that's what under the hood. So to sum up, Fluence develops the open applications platform, which consists of several parts. We have Aquamarine as the composability medium that controls and coordinates data transfer and execution transfer from peer to peer. On every peer, we have the Fluence compute engine that runs services compiled to WebAssembly. It uses interface types and multi-module linking under the hood. And finally, Fluence is everything together, combined to form the network. Blockchain is not yet implemented. We are planning to use a substrate for it, but it's to come later. So I'm ready for the demo. Evgeny, do you want to add something?
Yeah, just to sum up what Dmitry was saying about Aquamarine. Aquamarine is essentially the analogy of Kubernetes, let's say, like a scriptable analogy of Kubernetes, where you can have the scripts that fly over the network and bring data with them among services and essentially coordinate how business logic is designed between different services. Services run on WebAssembly, and all of this has security, like all decentralized required stuff like Kademlia and DHT to work as a public and secure network instead of just like how it works in private setups. And now Dmitry will show how we use an Aquamarine, how we follow this open applications paradigm and can build one app from another app with really easy additions to it, and how user experience can be dramatically changed if we just add, like recompose and add a little bit of new code.
Thank you, Evgeny. So switching to the demo. Let's build the chat application. Chat application is when we have different people, and people can send real-time messages, and other members of the chat can see these messages in real time. So first of all, let's decompose the chat application into a set of services. For the simple chat, we have just two services. The first service stores messages of the chat so that a person who joins later can see the history. It's the chat history service. And we also have the user list service to have all the users and to notify them about the new messages. Here we have the same on the network map. We have clients. For example, this client in a browser. We have two peers, and we have a service for the user list, which stores members, and we store messages in the history service. How could the composition, what could the composition look like? When the client sends the message is stored to the history service. Then in order to broadcast the message, we need to fetch users which are the members of the chat. We have the list of users, and then we call the function to display the message on all the other clients. So let's take a look how it works. Here we have the chat application. I'm already joined. I'm a zebra, and I can say like something. Here we have an error script that was emitted to the network and executed by the Fluence nodes and by the other peers who joined the chat as I did. And I can reply to some message, send a reply to the folks that loves Fluence. Nice. So here's the reply. So nice. And actually it was coded just in a couple of hours. But what is even better is that from the chat app, we can do, for example, a feed app or a channel app. For example, in Telegram, we had these channels when we have messages from a particular author authorized to send messages, and we have many subscribers to get these updates. So essentially, feed is the chat with the authorization check, so that we still can use the user list service for subscribers. We can take the chat history service for messages and change it to make up the feed history service by adding some part of authorization here. And if we wrap up these two services and deploy them again, we will have the new application, the feed application. The interaction here is very similar. The only change is that we store posts in history, we store subscribers in the user list, and here we check if the client that tries to store the post is the owner of the service. And then we have the same interaction for broadcasting posts. Let's take a look on the demo. Here we have the feed. I'm the camel. And here we have only posts from the camel. I can add the post as a camel. It's handled with just the same air script, and I can add data here. I can spread my thoughts to the world. Nice. Finally, let's take both and let's augment the feed with comments to have the blog application. So blog essentially is the feed or a channel with comments. And to make the blog, we can reuse the chat history service to store comments here and to make comments history service. And we can reuse the already deployed feed application so that there we already have the author, we have links here, we have content, and we just want to extend this open application with comments independently. So the network map will look like this. We have all the same services from the feed application, which were already deployed. And we deployed a new service, history service, for the comments. We can store comments like replies to the posts stored here. We can get comments, and we still have all the other interactions. We check the owner and so on, and the old UI still works. The old application still works. We still have activity of authors here. We still can send the posts. We still broadcast posts. Just add some new UI for the comments. Let's take a look on the third demo. Here we have the same feed, the same content, but now I'm not authenticated as the camel. I'm not the author that can send messages, so I don't see this at post fragment. But if I say something, it will appear here. But now I can choose the post, and I can add a message as a monkey. Hi, I'm a monkey. Send a comment, it works. Oh, and we have some other comments here. Hello, Camel. Hi there. So to handle this, we slightly changed the error scripts and reused the previous deployment of the feed application. So it was pretty easy. But finally, we have two different applications, two different layouts, reusing both code and the data and the users. So just to recap, I demonstrated full stack application. We have front end and we have back end. For the front end, I used Yelm UI, and I have error scripts. So the choreography is expressed on the front end, and the scripts are immediately sent to the network to be executed. For the error scripts, we have a Fluence JavaScript SDK, actually TypeScript SDK. And we run WebAssembly error interpreter in the browser. So it's the same code on the front end on the back end for interpreter. Just to recap, error is Aquamarine intermediate representation, a low-level language. On the back end, we have deployed several Fluence nodes. We use Kademlia under the hood to find the peers by public keys. We use DHT to register peers and relays and to route to clients, from clients to clients. And on every node on the back end, the Fluence compute engine is being running. It runs error interpreter compiled to WebAssembly, and it's running in FCE. And then we have multi-module services for history and for user lists. Each is built from SQLite compiled to WebAssembly and from some business logic. This demo is available on GitHub. You can take a look on error scripts and you can try to compile it, file issues, and so on. And also we have Fluence, FCE, and Aquamarine source code opened. You can take a look on it. And finally, this demo is live right now. If you open this link, you will see the chat that I was using just recently. So let's play with it. And if you have any issues, please file them. Thank you.
Great. So thank you, Dmitry. We hope everybody understands the power of what that is and how easy it is to create those applications. You know, we showed those are chat apps. We thought Fluence isn't designed to build chat apps, but it's the easiest and most intuitive way to show how applications can be built one on top of the other and how features can be added. And so we thought that was an appropriate demo to kind of demonstrate very quickly and simply what can be done. But if you really think ahead, we think this composition could enable applications that historically have had no relationship to each other whatsoever to combine components. And so you could see a message service combined with, you know, maybe a transportation, you know, service, or, you know, healthcare combined with banking. I mean, there's a variety, whole different ecosystems could compile and use the same pieces together. So how do we get there? And so we're launching today the Aquamarine network. This will be live in a week or two. So you've seen it, it works, but we'll alert everybody here when you can actually use it, which is just a week or two away. And then next year, around summertime, we're going to launch the economic layer, which is a blockchain-enabled licensing system, which is what allows the economics to transmit throughout this network and allows rewards to happen for every single piece of this ecosystem. What are we doing next? Also, we're publishing 2 papers this year. We're going to publish our distributed computing protocol paper. Very excited about that. So look for that to come. And next year, we're going to publish our crypto economics paper, which describes in detail the economics and how that economic layer works, and how it's all put together. So those have pretty much been written. They're just some final touches finishing on them right now. We're actively hiring. These are 4 open positions right now. We'll be adding more positions over the coming weeks. So apply to Fluence, fluence.network/jobs. These are the open positions, all developer focused. If you are interested in joining us, but then don't fit any of these particular roles, certainly reach out, because we have a lot to do and we're going to need to fill a lot more roles. We're a distributed team, so it doesn't matter where you are. We just want really motivated, hardworking self-starters who believe deeply in what we're building. So thank you for that, and really appreciate everyone's time. And I want to turn to Evgeny to talk about kind of the UIs that we're building.
Yeah, so the whole idea of Aquamarine is to make the composition and creation of new applications really easier and make time to market really faster. So to create a new product, you don't need to re-implement all the other stuff. You don't need to host all the other stuff. So you just build new features and compose them to existing services that have been run by other people already. But to make this even easier for developers and to make an onboarding process easier, we are building the web product, which will have all this functionality, like to see what services exist on the network, what is published, what nodes exist, and we'll allow to write Aquamarine scripts and test Aquamarine scripts in the browser. So everything is coming. We will separately announce when we launch this product. Should happen sometime in between our big milestones. And
so thank you for your attention. Follow us on Twitter and on Telegram. And we're going to pause for a second and start to address some of the questions that we've got. Thank you. So I'll turn it back to Evgeny to address some of the technical questions that we received.
Okay. First one, how much faster is it to build on Aquamarine? As Dmitry showed, as Dmitry showed in the demo, you really need to change, to tweak a little bit existing services if you need, or just use services that are already deployed in the network and write these Aquamarine scripts. And for writing, obviously, we're not expecting most of people writing this low-level air script with brackets that Dmitry shown. We have JavaScript SDK that abstracts out a lot of this complexity and makes really easier writing on Aquamarine. Dmitry, you want to address anything?
Well, first of all, about Aquamarine. I have shown the low-level language, and it should be the compilation target for the higher-level languages. And we're developing the Aqua language that will compile to air and will abstract out some patterns of air programming. Then, what does it mean? How much time it takes? With all this infrastructure that we are developing, the developer can use external services through WebAssembly adapters, which we haven't covered today. You can reuse modules, WebAssembly compiled modules developed in different languages, different frameworks, and bind them together in multi-module setups. And if you want to change a service just a little bit, you can just pick the module that you want to change and change it or rewrite it in the language of choice. If you have many modules and many services to deploy, you can just reuse them, redeploy them. If you have the ability to open the code for composition, which is usually hidden in private deployments, if you can share it and reuse it secure way with Aquamarine, then you can also have these parts to speed up. And finally, if you have the application which is running and all you need to do is just a slight addition to this application, you can preserve the user base, preserve the hosts, which is running applications right now, and it should also bring a huge benefit. So we have many layers of composability and efficiency here.
Okay, awesome. Next question, what can we build besides the chat app? Yeah, obviously, I think we addressed that already. We envision Fluence as a engine for building all kinds of applications, like all kinds of web applications. Like you can build Zoom on top of it. You can build all kinds of stuff that you're using on the web every day. But maybe it's not even limited by the web. Think about IoT and all, all this software. Basically, most of software that we use today is software that is distributed, right? Like we have components of software talking to each other over the network. It might be different devices that talk to your phone, or it might be like a manufactured devices. It might be my laptop talking to your laptop, many combinations of that. And like the amount of devices we have in personal life and in industry grows every year. So all software becomes network software, and all software becomes distributed. And Fluence empowers the software with easiness of building and composition. That's the idea. You can build anything. You can build web apps. You can build not only web apps. Probably next question. So how do I run my code on the Fluence network, and how can other people use programs I have developed? Again, you need to publish your application into a network, and the way how it's gonna work, you will be publishing the application configuration, sort of like your application data and your authorship and the dependency tree on a blockchain. So this information will live on a blockchain, will be always available, globally discoverable, and immutable. So when you publish your application, you publish this thing on chain, and the code, the compiled app, lives off chain. So you just publish it to a network. It lives in network DHT, distributed hash table, which is kind of distributed storage for those kind of data. And then it needs to be picked up by hosting providers who run Fluence nodes. And you can be hosting provider for yourself if you want. So you can run a node and you can provide your application for users. But then again, you're not like, you have this link between authorship and ownership. So probably you would want other providers to host it for you. And how other people can use your code, there will be a way to discover what applications and software components are available. One way to discover is to use web product that we will provide, but there might be many web interfaces or listings that will feature some particular apps or components to discover. So this works exactly like internet. Like there are many websites, up to 1 million websites. How do you discover them? You discover them through search engines, through linking from one website to another website, from friends. Somehow, this is also the way. But we will provide the initial ways to discover what's in the network, like what is available. And also, like other scenario is, imagine that some application becomes really popular and you know it's on Fluence, so you start building on, like you want to offer new feature for users of these applications and attract even more users. So you will just know that what is on Fluence already and what is not. Tom, Dmitry, you want to address that as well? Tom, you muted.
No, Evgeny, I think you covered it pretty well. I have nothing to add on that.
Okay. Next one. How do you exactly use interface types in services? And can you pass data between modules with IT support? Dmitry, IT means interface types. Dmitry, you want to address?
Yeah, we use interface types two ways. First way is we do linking with the interface types. So you can take several modules and combine them together to make a single service. And we have a shared nothing linking scheme. So you can pass different data, records, strings, vectors between modules using interface types. The second way is we are using interface types to express the external API of services. So when you call functions, service functions from Aquamarine, effectively it goes through interface types as well. You can take a look on the repo, and probably you have some talks by Mike about FCE. It's a huge topic and really nice topic.
Yeah, I think we can shoot you links about like these talks about FCE by Mike and like all the related links. Next one is I don't understand what is service and how it's related to WebAssembly. So as we were saying, like modules are essentially the compiled WebAssembly packages. So for example, I can have SQLite database compiled to WebAssembly. So this is a package and this is a module. I can have authentication module near that and combine them together. I can create a service which will be available on the network. So service is something that exposed to a network. So when I have SQLite module and authentication module combined, I have the authenticated SQLite that I can expose to a network. Because unauthenticated, the SQLite without authentication, it really just doesn't make sense to export to the network because everyone can just write into it. So you need few of them to create a service that makes sense. Like I can have database, authentication, backend, or backup, and some business logic that would explain like a data formatting into the SQLite. So we'll have like 4 modules together forming a service, and this service will be like a chat history service or whatever business logic I code into one of the modules. And that might be like really different ways how you compose it and create services. But it's really modular. It's really easy to recompose all of this. And you can just reuse compiled packages, even with state. So if you have some module that contains state inside, you can just reuse it to create a new service. Dmitry, anything here?
Well, you covered the concept, and just to add an example, for example, we have history service for messages, and we have a user release service. Both use the same module for SQLite, but with different data schemes and with different APIs. Like we have get replies to fetch replies on the history service, and we have get all users on the user service. So really, SQLite is not secure to expose to the public network, but it's very useful as a module. And in Fluence, you can combine them together to make a service which is public.
Awesome. Next question. I have my backend APIs and want to compose it with third-party APIs. Is there a way to do that? Yes, if all your, if your backend APIs and external APIs connected to Fluence network. So every API needs to be exposed on a Fluence level. And what does it mean? You can build the WebAssembly module, which we call adapter or connector, which would be connected to external world, essentially, or the network, or just over the external world in terms of Fluence. So it may maybe use some data from your from the server where it sits through WASI, and Mitri can talk more about this. But the whole idea is you have these adapters sitting where your APIs are, and you use Fluence network and all the Fluence features between them. But you need these adapters to connect existing services. Dmitry?
Yeah. Well, essentially, interface types is the key here. So to use external API, you need to lift it and express it in a WebAssembly interface types by making the WebAssembly module which exposes it. And there are many ways to do it. And we have two built-in ways. First way is to call the daemon. For example, we have the IPFS module that can send files and receive files from the IPFS, and we call it the effector module. It has slightly different security guarantees and approaches. So you can use the local daemon for something that runs on your machine. And also, if you have an external API, you can simply call HTTP, make a HTTP requests. For example, we have an effector for CURL or curl, so you can just call external services.
Okay. There was a question regarding the repository, Aquademo repository. It is not public. It should be public right now. Try to check once again. It seems like we just made it public during the stream. And the next one, will there be a way to make requests of the developer community? I'm not sure what does this mean. What kind of requests? Pull requests or something like that? I mean, if this is a question about pull requests, everything we do is fully open source. So we are happy and excited if you participate, if you contribute. We'll be doing more and more, standardizations and guidelines. Right now it's a little bit chaotic, but we are working on documentation pretty heavily right now. So it will become easier and easier to participate. And we are really it's open project. It's open source. It's open network. It's something like, Aquamarine. You can think of Aquamarine something like HTTP specification, right? Like something network, low-level stuff. And we obviously happy to have contribution to that. We happy to have contributions to all kinds of tools around it. So we just initiate this, but we definitely long-term to build a huge community around it and to pass the power to the community. And that's related to, oh, maybe that was related to governance question, actually. There's a question about governance. What is the long-term governance plan for the Fluence network? And Tom, I think you want to address that.
Yeah, so with regard to governance, what we're thinking about here is the oldest and most tried and true governance model in the ecosystem, which is obviously that of Bitcoin. And I think that is most likely the path where we start off with kind of some of the team here. We involve the community, and over time step away and have it be community led and community run, and managed in that kind of informal process. So we're not, it's easy, and I think everyone understands what we mean by that. What we're not doing is a complicated on-chain governance system. I think that's something that we feel is untested and has a variety of complications associated with it. And we're also not doing kind of a council type model as well for different reasons. But this is designed to be collaborative and community focused. And so we're going to follow the model of kind of the oldest and most successful collaborative community focused model out there, which is that of Bitcoin.
There is a comment around requests in sense of business needs, but I still don't get it. What does this question mean? Like just write it please again, or if Tom, you know what this question about. Okay, let's skip it for a second.
Evgeny, about the requests, please reach out to us and let's discuss it.
Yeah, just reach out to us in any uncertain situation, reach out to us. Okay, next question. What is the main requirement to become a Fluence developer? To know the Rust language? If you want to build on Fluence, you may do different things. You may want to just like create applications. So when you create an applications, you can reuse ready services. And at some cases, you don't need to know anything about the backend at all. But in most cases, you want to implement some new backend business logic. So you would want to create new backend services from existing backend services. So you would want to write a new code. Essentially, you need to package your new code as a new module compiled to WebAssembly, and then that runs inside the service that exposed to a network. So that module compiled to WebAssembly can be written in anything that compiles to WebAssembly. Right now, like full support of WebAssembly, best support is Rust and C++. We write everything on Rust. So I think Fluence internals are mostly Rust. So that's good to know this language. But the end goal is when a lot of backend components created by community who know Rust or know C++ or know new languages that will be added to WebAssembly, then at some point you will just would need to build just a front ends, right? So you would use JavaScript, you would use Fluence JavaScript SDK, and you would use front ends or like build front ends of your applications, and you will be just recomposing existing backends. And I think Dmitry had also additional thoughts on this, on the facade modules that we have in services and language that's required to build that.
Well, right now, actually, only Rust is fully supported for everything, and partly C++, but it takes much more effort. But it's about a backend, and ideally, the developers who develop backends may develop backends on anything, and at least provide the adapter for the backend, even running in, I don't know, Docker container or anything. So it should be rather easy to provide almost anything already developed to the Fluence network to benefit from composition and security model of Fluence network. And to build on the front end to make applications. To make applications, probably the developer will need to get several services and make a kind of boundary around them, the logical boundary, by just mentioning them in the Aquamarine scripts. And all of this is front end. So the front end developers can do full complete applications with all needed experiences by just adding the experiences and calling services from the backend. And finally, the application is the UI, some integration logic on the front end, and the configuration, like the front end developer can explain what is needed to be available for this application to be deployed and to be running and to be available. And then this package can be distributed and anybody can run the backend for it.
Great. Quick question on documentation. So as I said, the documentation partly exists already. There is some documentation on Fluence Compute Engine. There is a very brief documentation on Aquamarine, but we'll be more just working on it just in real time. And the paper also, the protocol paper, it's in a draft mode right now. We are trying to publish it as soon as possible. So subscribe to our newsletter to not miss it. I mean, it just describes all the protocol and all the components on paper, which is very cool. What else? We have a question about how join from Aqua Slides work, and do we have a special instruction for it? And maybe, Dmitry, you can even share slides back and show, or you had the specific slides about join and other instructions.
Let's take a look on it. So I have many additional slides. So a quick brief about AIR. AIR is as something like as expressions. It's like WAST, the text format of WebAssembly. So we have instruction, we have arguments for locating the function, locating the peer, locating the service, the function, and then we have arguments and result. That's the call instruction that says that execution should be moved somewhere to be done. And then we have the result. And then we have several combinators. Yeah, Aquamarine is backed with the p-calculus theory, the process calculi. And we have several combinators from p-calculus. First of all is sequential execution. And the contract for sequential execution is, first of all, we call the first branch. And then we can use all the outputs of the first branch in the second one. There could be only two branches. So if we have parallel instructions in the first line, then we can use all the outputs of all the parallel branches in the second branch. We have other combinators like parallel calls they cannot share data, exchange data, and so on. There is no synchronization. We have branching with XOR. We have a default for iterations. And let me show you one more picture in the repository. The Aquamarine repository. So the error script is executed on the node, and when the client or the initiator of the script sends it to the network, it becomes a particle. This particle contains both script and data. Script is immutable. Data is augmented by the peers involved into the interaction. The particle comes on the node, and it tries to execute as much instructions as it could. And if it realizes that there are different parallel branches which have not sent this particle here, then it does nothing. So effectively, we have several branches of execution for parallel execution. And then each branch has no knowledge about others, whether they finished or not, and what have been done. And they all send their results to the next node expressed just in this sequence. So when the next node combines the results and has everything needed, it executes the next instructions. Right now, there's no way to express things like I want to have only the first. Oh no, the first probably I can, but like I want to have 3 fastest results out of 5 trials. Right now, you cannot express it. It's not implemented yet, but I think in a couple of weeks, you will be able to do such scripts as well. So finally, there's no custom instruction for joining because it's just the contract of sequential execution. But we support joining and some logic above joining. Evgeny?
Awesome. There was another one. How does input-output works? Do the client needs to do the I/O himself, or he can trust it? Do you have some kind of general purpose oracles? Do you want to address that?
About inputs and outputs, we have several considerations. First of all, Aquamarine can call functions on the peers, including the client, including the browser. And it can ask client or ask peer for the data. And it's secured with the signature. So we know what data comes from what peer and from what method. For example, if you do authentication, you can have a dedicated service that have a function called is authorized or get role that returns a string. And in other services, you can check that the string that says that this user is admin, for example, is actually the role that derived from the right service. So we have the pool model for data. And we always preserve these security data signatures and Merkle proofs between service calls so that services could just trust the guarantees provided by the Aquamarine as a platform. The second thing here is a quite sophisticated thing, but we have different layers of coordination in Fluence. For some purposes, it's useful for the whole network to coordinate, like security and accounting. For some problems, it's nice to use Kademlia neighborhood and eventually consistent things. For Aquamarine scripts, we have involved peers, and for execution, we have a single peer coordination. So with Aquamarine as is and with Fluence as is, you can express any kind of arcalized logic you want, because effectively the call, a single call, is being done by a single node, a single peer, and the response is verified by a single signature. If you want to have the oracle, you can have a big number of peers, for example, querying the same API with the weather or Bitcoin price or whatever. And you can write a script that you want to select 500 nodes or 50 nodes or 5 nodes random that provide the service which is called Bitcoin price, and you can query them and you can trust, for example, 2/3 or something like that. So as an answer, there's no single solution for oracles in Fluence because coordination for a single call is done on a single peer because it's efficient. But you can express everything you want with Aquamarine and have these oracles. I hope the community will build some. Have I answered, Evgeny?
And I think related to oracles, as I explained earlier, like Fluence adapters or like connectors are essentially oracles to external world. So you can connect external APIs, external file system, external decentralized storage like IPFS, Arweave, Textile, like Fission, all of these projects, you can use them for backup of applications that built on Fluence, or not just for backup, but to store some data, to store some data structures, and you will be able to connect your Fluence applications to this decentralized project or to centralized project. You can connect to centralized API. You can connect to, for example, if you have something like, imagine CockroachDB, like with many instances of nodes, and the thing is distributed by itself and stays at some data center and controlled by someone. But if you need it, the data that kept there as a part of your application, you can have a connector to CockroachDB and expose this database to Fluence network. So connectors are some kind of oracles.
Great. Well, listen, we appreciate everyone's questions. I think we've got to wrap it up now. The one question line we haven't gone into is that of financing, and we're going to make an announcement about financing in the coming weeks. The other thing we'll say is that with regard to coins, coin economy, we're going to address all of that closer to our blockchain launch. So stay tuned for more details on everything related to financing and coins, because we know it's important to many of you, it's important to us as well. And we'll address it a little bit later in a different forum. So thanks very much for all of your attention, for all of your questions, for all of your interest. Please get out there, tell other people about Fluence, follow us on Twitter and Telegram, and start building. And let's see what we can do here. Thank you very much.